Hello everyone, welcome to the second lab report on motion of a falling object. So in this lab, I experimented with the motion of a falling object and the different forces acting on the object and collected the resulting relationship between position and time. The fundamental physical principles used in this lab are Newton's second law, which is net force equaling change of momentum over change in time. And from Newton's second law, you can derive the updated position and velocity formulas, which we did later in the lab. So we also have weight force, which is just gravity, and it's mass times the gravitational constant, 9.8 newtons per kilogram. Then there's also the drag force, which is the proportionality constant times velocity squared times v hat. And finally, net force, which in this situation is the weight force or gravity plus drag force. So my process was that I first observed the falling object, which was a crumpled piece of paper using Tracker, and I gathered the position versus time data from Tracker. Then I created a computational model using the provided GlowScript code, but with only gravity acting on the paper, only accounting for gravity, and then I collected that data. Next, I created a computational model using GlowScript, and this time I accounted for gravity and drag force and collected that data. And then I used Google Sheets to create a graph plotting all three position versus time models, and I compared the results. And then finally, I answered the additional what if and why questions. Here is the video that I imported into Tracker. I trimmed the video down so that it started and ended only when the object was falling. And on the right, we have all the position versus time data. And from this data, we were able to get the initial position, the initial velocity, which is just 0 in this case because the object started from rest. And we can use this data for the graphs. So yeah, here's some of the resulting data that I just mentioned, but using this data, I constructed two computational models with GlowScript, one with only gravity acting on the object and another with both gravity and drag force. So it is rather hard to see in this slide, but using that starter code from GlowScript, I input the following information. So I put the mass of the paper ball, I input the initial position and velocity vectors. I changed the time in that while loop to match the time of my video. I put in the weight force formula. I set the net force equal to the weight force because we're only accounting for gravity here. And then I updated the position and velocity formulas. And as a result, I got a 3D model of a paper ball falling. And then underneath that, we got the position versus time graph, we got a velocity versus time graph, and we got the coordinates for position versus time. All of this in GlowScript. So for the gravity and drag computational model, I put the following information. So the mass of the ball, the same thing, the paper ball, the initial position and velocity, which are also the same. What's new though is the proportionality constant, since we are accounting for drag force here as well. And we got the proportionality constant from just guess and check. So we had to make sure that the final position in Tracker was the same as the final position from GlowScript. And then I counted for change in time again to match the length of my video. In that while loop, we have the drag force. We had to define it with the formula. And then net force will now be equal to weight force plus drag force since we're accounting for both gravity and drag. And then I had the updated position and velocity formulas just like I did in the last model. And as a result, I got a 3D model of the paper ball falling with the position versus time graph underneath, followed by the velocity versus time graph, and the coordinates for position versus time. So here are all three graphed. The blue line is the observed model of that paper ball falling. The red line just is the model that only accounted for the weight force, and the yellow line is the model that accounted for both the weight force and the drag force. So I noticed that only using weight force creates an inaccurate model. As you can see, it falls off a lot faster than the observed model does. So I concluded that incorporating both weight and drag force allowed for the model to be the most similar to the observed model. Many of these models predict a terminal velocity. Terminal velocity happens when the force of drag pointing up has exactly balanced out the force of gravity pointing down. This means the net force will reach 0, causing constant velocity. So in other words, the model that included drag force as well will be the one to predict terminal velocity. And as you can see from the velocity versus time from the computational model that included drag force, velocity is reaching 0, and it's because of that drag force. Here is the what if question. Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The initial velocity is irrelevant when it comes to whether or not an object will reach its terminal velocity. The forces acting on the object will cancel each other out regardless of initial velocity and will in turn reach terminal velocity. Thank you.